Hello and welcome to our last lesson of Unit 5 on vectors and applications. Today we are looking at the application of the cross product, and it is a shorter lesson, but please make sure to complete any practice questions from previous lessons if you haven't done so. And just familiarize yourself or review all the concepts we learned so far. Our next lesson is the summative assessment, and we had a lot of new information for this unit with vectors. So review any of the simulations if you need to, any of the extra readings if you need to make sure you're fully prepared for our assessment, which will cover all the things we have learned so far. So today we are going to use the cross product, and I've already listed some of the applications for you, starting with the area of a parallelogram, and also to solve some real-world problems, including vector quantities such as torque. So by now you've seen area of a parallelogram, or we've seen the parallelogram method used, but now we're going to find the area of a parallelogram using cross product. So let's say we have a parallelogram A, B, C, D, and it's formed by the two vectors A and B. So this is just also A, and this is vector B. There we go. This is vector A, and this is also vector B that forms the parallelogram. And we have angle theta, which is the angle between vectors A and B. So the area of the parallelogram is going to be the cross product of A and B and take its magnitude because remember, area is a scalar quantity. This is also equal to the magnitude of A times the magnitude of B sine of theta. And I want you to think about why this is true. So remember, to find the area of a parallelogram, we have to kind of treat it as a rectangle. So we have to find this height here and multiply it by the base. So this would be the length in a rectangle, and this would be the width. But to find this, that's why we have to use the sine of theta, and we find this height times the base, which is magnitude of A. So the height is magnitude of B times sine of theta. And so then when we multiply them, we have the area of the parallelogram. But now we're going to show that this is actually true, so that if we find the cross product of A and B and take the magnitude, then this is the same as this value here. And so this can help us, for example, if we aren't given the angle and we just have A and B in component form, then we can also find the area. So here, starting with the cross product A and B, and this is the formula we saw last class, then taking the magnitude of this squared, and this is just using the magnitude of a vector in three-dimensional space. So we take the x component squared plus the y component squared plus the z component squared. And so if I wanted just the magnitude, I would have to take the square root of all of this. But we're not going to do that just yet. So first I'm going to expand and factor. So what I'm really doing is I'm expanding this with respect to the square, and expanding this and expanding this. And you can use what you know about square of binomials here. And if we factor it as well, we end up with a1 squared plus a2 squared plus a3 squared. And this is times b1 squared plus b2 squared plus b3 squared. And subtract, we also end up with this term, a1b1 plus a2b2 plus a3b3 squared. Now, this value here, and I've broken them up here, is the same as the magnitude of a squared. And the second part, with all the b's, is the magnitude of b squared. And this value here, which is a1b1 plus a2b2 plus a3b3 squared. So actually just the value inside without the squared was from the dot product, right? That is the algebraic form of the dot product, or the dot product for algebraic vectors, which was the first two terms multiplied plus the second two terms plus the third terms, and all of that added together. So this was the dot product itself, which is magnitude of A times magnitude of B cosine of theta. So now I'm just going to rewrite all of this in terms of these new definitions. So I have magnitude of A squared times magnitude of B squared, and minus here magnitude of A times magnitude of B cosine of theta. And I can now see that if I distribute this squared here, I have A magnitude of A squared, magnitude of B squared, and cosine of theta squared. So I actually have the A squared, or sorry, magnitude of A squared times the magnitude of B squared in common in both of these terms. So I factor that out. In the first term, I just have 1, and in the second term, I have cosine of theta squared. But 1 minus cosine of theta squared, and this is from the one of the identity properties for trigonometrics, or identity properties of trigonometry, we have that this is equal to sine squared of theta. And remember, this is because sine squared theta plus cosine squared of theta is equal to 1. So then I have this, let me just highlight it for you. We have this on the left-hand side and this on the right-hand side. So now taking the square root of both sides, this one is just the magnitude of A cross product B because it's just going to be positive anyway, so it's positive. But this side we have the plus or minus of magnitude of A, magnitude of B, and sine of theta. But remember, in a parallelogram, we have the theta is between 0 and 180 degrees, or generally when we're working with vectors, we have this property that we've been working with. So then for these values of theta, sine of theta is greater than or equal to 0. So then we don't need to consider the negative value here. So then the magnitude of the cross product of A and B is just the magnitude of A times the magnitude of B times sine of theta, which is, again, what we were trying to show from the beginning here. And so now we actually have a way that we can, or a formula for how we can find the magnitude of a cross product without necessarily the whole procedure with the cyclic algorithm that we saw last time. So if you have the magnitude of A and B and the angle between them, then you can, or even if you have just the two vectors, you can easily find their magnitudes. And if you have the angle between them, then you can find the magnitude of the cross product. Now, let's do an example. Here we have a parallelogram formed by the vectors P, which is 2, -1, 4, and Q, 1, 3, -2. And we're asked to find the area of this parallelogram. So from above, we know that area is equal to the magnitude of the cross product P and Q. So first we set up the algorithm here. So -1, 4, 2, and -1 for P. And for Q, we start at Q2, which is 3, and then -2, 1, 3. So taking the cross product here, we have -2 times -1, which is just 2. Take away 3 times 4, which is 12. And then 4 times 1, 4, minus 2 times -2, which is just 4 now, plus 4. And then 2 times 3, 6, minus 1 times -1, or just plus 1. And this gives us -10, 8, and 7. And so we can see that the cross product here, if we take the magnitude, it's going to be -10 squared plus 8 squared plus 7 squared, and it's square root of 213, which is approximately 14.59. Now, keep in mind, again, with vectors, we don't have, we aren't necessarily given units, but we are now working with area. So we do have to acknowledge the unit for area. So we just assume that the side lengths have a magnitude of unit. So then unit times unit is going to be units squared. So our area is 14.59 units squared. Now, if you were given the angle here, you could have done a double check here to find magnitude of P and then magnitude of Q and then sine of theta, and we would have seen that this would have been the same as this value here. And so now a question for you is, how can we use the area of a parallelogram to find the area of a triangle? Because you can be given, for example, two vectors and told that they are connected to form a triangle, and what is the area of that? So how could you find the area using what we just saw? So consider a triangle, and it is formed by, a parallelogram actually, starting with, let's say this is vector A, and this is vector B. And now I can copy this, and then copy this, and I have the parallelogram form. But now I'm going to divide this into half, and this is now my triangle, and it is formed by vectors A and B. So ultimately, if I have the area of the whole parallelogram, this whole space, and if I divide it by 2, then I really have only this area, or sorry, okay, there we go. Okay, then I have this area, which is the area of the triangle, which is what I wanted. So essentially, you start from the area of the parallelogram and you divide it by 2. Now we're going to see another example for that triangle, but instead of being given the vectors, you're given the 3 points of the triangle. So here we would have point A, B, and C. So essentially, we have to find vector AB, and we have to find vector AC, and then we can find the area of the parallelogram that way. So starting with vector AB, this is just going to be point B minus A. So this is 4 minus 1, 0 minus 2, and 2 minus negative 1, which gives me 3, negative 2, 3. And this is the vector AB in component form. Now, similarly, we can find vector AC, which is C minus A. So then we have 2 minus 1, 5 minus 2, and 3 minus negative 1, which is 1, 3, 4. So now I have my 2 vectors, and I can find the area of the parallelogram. And the parallelogram is AB and AC. So we find that cross product there. So starting with my cyclic setup, so I have this is vector AB, this is vector AC, and we can find the cross product. So negative 2 times 4 minus 3 times 3 is going to give that negative 8 minus 9. For my y component, I have 3 times 1 minus 3 times 4, which is 3 minus 12 here. And finally here we have 3 times 3 minus negative 2 times 1, which is, yes, 9, take away negative 2, and we end up with negative 17, negative 9, and 11. So now we find the magnitude, which will give me the area of the parallelogram. So the magnitude will be negative 17 squared plus negative 9 squared plus 11 squared, and if we take the square root, that is the square root of 491. Now the area of the triangle is going to be half of that. So half of square root of 491 is approximately 11.08. Now, same thing here, we have area, so we do need to give it units, but because it's arbitrary units, we just put 11.08 units squared. So that would be the area of the triangle formed by these 3 points. And if they had given you the vectors as well, you would just do the same process, find the cross product, find the magnitude, and divide it by half. But I did want to show you this option as well because some of your questions, you will be given the vertices and you have to determine the vectors yourself. This can also be applied for parallelograms. You may be given the points that form the parallelogram, and then you have to find the vectors and the cross product to give you the area. Now, we're going to look at some real-world applications of cross products. So yes, it can help us with area of parallelograms, but what about expanding it to the real world? So forces that involve turns or rotations about a point or axis make use of the cross product. So some of these examples, and these are just a few, there's probably a lot more examples that use the cross product. But for example, tightening or loosening a bolt with a wrench. So this one, I actually have a diagram for you. Here you have your bolt here, and this is your turning point. This is the point which you're turning about, and the wrench is going to be where the force is applied. So you can turn up with the movement, turn up or down, and you're applying force upwards or downwards. And it's not directly downwards, it's more, it is a more diagonal angle which you are applying the force at. And we also do have to account for how long the wrench is in this example. And this would be a case of cross product here. You can also think of rotation of the crank arm on a bicycle as you pedal. You can think of using a screwdriver where you're rotating about a certain screw as well. Engines and motor rotations often have turns and rotations about a point. Pushing or pulling on a door is also think of the hinges of a door where that's the point which you are doing the turn. And another example as well could be rotation of a crane arm or robotic arm, which again, you have the point at which is attached to the machine, and then you are rotating about that point. So now let's see what that could look like. So of course we have M, which is our turning point. We also then have vector r, which is now the radius vector, and it is in the units rm. And this is the direction from the turning point M to which the point to the point that the force is applied. So this is where you're pushing. Thinking of this wrench, you can either hold the wrench really close here and turn it, or you can hold it from the handle or down the handle here and push it from here. And this will actually make a difference in the overall force and overall force that you're applying to the wrench. Then we also have to account for our force vector, which is how you're pushing it. So if it's the stronger you push, the greater the magnitude of the force, and also the direction which you are pushing. So are you again pushing this way or pushing this way? Now let's see where cross product comes in. So we have what we call torque, and torque is going to be the vector r cross product with F. And remember, this is same as when we saw the dot product. We have M and the force, or sorry, the units M and N. So the product of these two is joules. And this measures how strongly a force causes something to rotate. And its magnitude is given by, now we're using the definition of cross product here, magnitude of force or vector r times magnitude of the force vector times sine of theta, which is the angle between these two forces. So in the wrench example, a longer wrench would mean a greater turning effect. And sorry, this one should be turning effect, not turning point. I was looking at it and it was weird. Okay. Because your magnitude of the radius will be greater because you're pushing, because you have a longer wrench. And a stronger push would mean a greater force, so then magnitude of force is greater, which also means a greater turning effect. And that makes sense, right? When you push with a lot of force, then you're turning it also with greater force. So what that would look like in terms of our vectors, here we have our turning point M. This is the radius. So for example, this could be the length of the wrench, and this is the force that's being applied. And this is our angle that we are looking at here when we say theta. And this is now the resulting vector of the cross product of R and F. And in fact, this is actually going, so this is three-dimensional space, right? This is perpendicular here, and it is perpendicular to R. And it is perpendicular to this force F as well. So let's look at an example now. A mechanic applies a force of 120 Newton to the end of a wrench that is 0.35 meters long. The force is applied at an angle of 70 degrees to the wrench, and determine the magnitude of the torque about the bolt. So using the torque formula here, and we just want to know the magnitude. So we take the magnitude of the cross product of R and F. So the magnitude of R is the radius, which was 0.35 meters, and the magnitude of the force is 120 newtons. And we have sine of the angle, which is 70 degrees. So if you evaluate this, we get 42 times sine of 70 degrees, and this is approximately 39.47 joules. And so we say the magnitude of the torque about the bolt is about 39.47 joules. Now, how can we maximize torque? And especially consider that this torque is given by the magnitude of the radius and the magnitude of the force and multiplied by the sine of the angle. So to do that, we need to maximize both r and sine of theta. So this means, in this example, applying the force as far down the handle as possible to give us the maximum radius, and applying the force at a right angle, because sine of 90 degrees would be equal to 1, and that's the greatest value of sine of theta that we can get. And again, this is for theta between 0 and 180 degrees. Now, another example here, we have a driver applies a force to the edge of a steering wheel with a radius of 0.25 meters. The force is applied perpendicular to the radius of the wheel. Now, if the torque produced is 18 joules, determine the magnitude of the force applied. So now we're given the torque and we have to use it to find one of the other magnitudes, and in this case, the magnitude of the force. So since the force is applied perpendicular to the radius of the wheel, then theta is 90 degrees. So sine of theta is 1. So the magnitude of the torque is equal to the magnitude of the radius, which was 0.25. And we don't have the magnitude of the force, that's what we're trying to solve. And sine of theta just becomes 1. So then we have 18 is equal to 0.25 times the magnitude of the force times 1. So then the magnitude of the force is equal to 18 divided by 0.25, which is 72 newtons. So the driver applies a force of 72 newtons. Now, one thing I want to point out with, because it is in one of your practice questions, keep in mind that this radius is in meters. That's the unit of measurement we require to get joules. So if you're given centimeters or kilometers or any other measurement, you do have to complete a conversion to make sure you are using meters for this calculation to work accurately. And that is the last example of this lesson. So a short introduction to some of the applications of cross product, but again, there's many applications to vectors as a whole. And this was the last lesson of this unit as well. So please familiarize yourself or review everything from the lessons we've seen so far, and make sure you're ready for our summative assessment next class. And as always, don't hesitate to reach out if you have any questions, and I will see you all in our next and last unit.